This video is on basic shifts of a quadratic. Basic shifts are only going to be talking about how the a value and the c value affect a quadratic. There is also a b value in a quadratic of ax squared plus bx plus c, but that's more complex than just a basic shift. The vertex will affect the shifting as well. So this video is specifically talking about the a value and the c value of a standard form quadratic equation or expression. So first we have f of x equals x squared. When we have f of x equals x squared, the coefficient is 1, there's no addition or subtraction. This is called the parent function of a quadratic, because nothing is happening to it at the moment. So the parent function has nothing has been added or subtracted or multiplied or divided to the original equation. So we have just x squared. We have a 1x squared, so the a value is 1, and nothing has been added or subtracted. So the parent function, if we were to plug in numbers, we're going to plug in 0 for the x value. 0 squared is 0. So our first coordinate is 0, 0. Then if I plug in 1, the x value of 1, 1 times 1 is 1. So we have 1, 1 is our next coordinate. If I plug in -1, -1 squared is also positive 1. So I have my coordinate at -1, 1. If I plug in 2, 2 squared is 4, so then my coordinate is going to be 2, 4. If I plug in -2, -2 squared is positive 4, so we have the coordinate -2, 4. We can see symmetry around here now, so we can see that our vertex is at 0, 0. In a parent function, that should happen where your vertex will be at 0, 0 of a quadratic. So then when we plug in 3, 3 squared is 9, so we'll have the coordinate 3, 9. Now since we have symmetry, I should also have 1, 2, 3 spaces away from 9, 1, 2, 3 spaces away from the axis of symmetry. And we can check that. -3 times -3 is positive 9. So this is our parent function. This is when nothing has been added or subtracted to it. This parabola will go through the perfect squares. And it does continue onwards up, so we know that the range is going to be greater than or equal to 0. Y is greater than or equal to 0. So when we're looking at basic shifts of a quadratic, we focus on the a value and the c value. So if we look at f of x equals half x squared, we want to know what happens to this. We still have nothing added or subtracted, so if we plug numbers in, we're going to start with 0. 0 squared is 0 times half is still 0. So we still have 0, 0. Next, we plug in 1. 1 squared is 1, but then we have to take half of that, so we get a half. So my coordinate is not at 1, 1, but it's actually lower than the parent function was. Before we had 2, 4. Let's see what happens when we plug 2 in. 2 squared is 4, but we have to take half of that, so we end up at 2. So it's not going as fast as the parent function did. When we plugged in 3, we had 9. So if we plug in 3 here, we have 3 squared is 9, but we have to take half of that, so that's at 4.5. So we have symmetry the same way we had the symmetry on the parent function, where I have -1 is at a half, -2 is at 2, and -3 is at 4.5. Now I can actually potentially find another coordinate if I plug in 4. 4 squared is 16, half of 16 is 8, so we can have the coordinate 4, 8. That's another coordinate that we could get that we could not get on the parent function because our graph didn't have enough to be able to do the next value. So we can still do that. -4 is also at 8. So what happened to this? It definitely went slower with the y values. We plugged in the same x values, but our y values were not as high as the parent function. So our rate at which the y values are changing is slower. This has been almost flattened out some because of this half. This is called a vertical compress. If we were to look at both of these on the same graph, we would be able to see that the pink, this one right here, the half of x squared, is actually wider than the parent function. Sorry, I am wanting to show the pink on this graph as well. The pink is wider than the parent function because it is compressing. It is pressing it down towards the x-axis because it's not going as fast. So this is called a vertical compress because the values are going slower, and that happened because we are multiplying by a half after we square the values. So what happens when our a value is bigger than 1? So the parent function had an a value bigger than 1. This problem had an a value smaller than 1. It was a vertical compress. What happens when it has an a value bigger than 1? So if we start with 0, we plug in 0 times 0 is 0, times 2 is still 0. So we still have our vertex at 0, 0, just like in the parent function. Then if we plug in 1, 1 squared is 1, times 2 is 2. So we actually have a coordinate of 1, 2 instead of 1, 1. Then we'll plug in the 2. 2 squared is 4, times 2 is 8. So it's at 2, 8, which is much higher than it was for the parent function. 3 squared is 9, times 2 is 18, which I cannot put on this graph. So let's do some symmetry. So the negative 1 will also be at positive 2. And then the negative 2 will also be at positive 8 because of the symmetry. So what really happened with this graph? This graph looks to be that the y values are going much faster or growing much faster than the parent function. So if we were to look at this on that parent function graph, we have to start at the same spot, but the rest of our stuff is going much faster. It's actually more narrow than the parent function. This is called a vertical stretch because it's going faster. This is going faster. It's called a vertical stretch. Because it's stretching, it's going quicker vertically, not horizontally. So it's wanting to go up faster than the others. So when there is a number in front of x squared, so multiplied to x squared, so the coefficient of x squared, if it is greater than 1, then the graph is, so right here, it's skinnier. Which means that the y goes faster. This means that it was that vertical stretch. This is the math term that we use, the vertical stretch. This is a way for us to remember what it looks like. It is more narrow or skinnier, so the y value goes faster on the graph. We call that a vertical stretch. So if we're looking at numbers that are less than 1, like this graph right here, we saw that it was actually wider than the parent function. The graph is wider than the parent function because the y value goes slower. Now the terminology we use for this is that we have a vertical compress because it's pressing down towards the y-axis. This is what happens when we have the a value is changed. This is a basic shift of what happens when only one value has changed. The a value, your leading coefficient, has changed from 1 to be smaller than 1 or to be bigger than 1.